As we are working with definite integrals, we'll need to know some properties to help us. So at the end of this lesson, you'll be able to use the properties of integrals to evaluate definite integrals. All right, you'll notice the properties of definite integrals. The first one is just saying if as long as x is defined at x equals a, then the integral from a to a of a function is equal to 0. That basically is true because if you're going from, you're really not moving, you're not covering any area at all, so of course the area under that curve would be 0. Okay, if f is integrable, you can take the integral. Then if I have the derivative from the integral from b to a, it's equal to opposite the integral from a to b. So if you switch the endpoints, you switch them around, then you actually have to take the opposite of the integral. Okay, the third property is if we're taking the integral as long as it looks like we're integrable on 3 closed intervals, the integral from a to b would be equal to the integral from a to c plus the integral from c to b. So it's talking about something like this. If I'm going from a, we've got a, b, c here, and let's say we've just got this curve right here. It's just saying that if I go from a to c and then c to b, and I add those two together, it would obviously give me the area under the curve from a to b. And then the last one, if f of x is continuous, then it is integrable. So this one, we don't worry about sharp turns or anything like that. As long as the function is continuous, you can take the integral. So let's go ahead and use these properties. Right, the first one, it tells us that the integral from 0 to 3 of a certain function f is equal to 4, and the integral from 3 to 6 is equal to -1. And then in part A, it asks us to find the integral from 3 to 3. Well, since we're going from the same x value to the same x value without even caring what the function is, it automatically will equal 0. Okay, if I'm going from 6 to 3, I notice that I have an integral that goes 3 to 6. So I know this integral from 6 to 3 will be the opposite of whatever the answer is from 3 to 6. And we know the answer from 3 to 6 is -1, so it's going to be the opposite of -1, which will equal 1. And then the final example, if I would like to find the integral from 0 to 6, what I'm going to do, I notice that I know from 0 to 3 and 3 to 6, so this will actually equal the integral from 0 to 3 plus the integral from 3 to 6. And I notice that the integral from 0 to 3, we know that that is 4. The integral from 3 to 6 is -1, so 4 plus -1 is 3.
Right, example D, find the integral from 0 to 3 of 4 f of x dx. Well, if you recall from the properties, if there's a 4, if there's a constant, we actually can just bump it out front and we'll multiply our answer by 4. So this really just means 4, the integral from 0 to 3 of f of x dx. All right, they gave us that the integral from 0 to 3 f of x dx was equal to 4. So this whole part is equal to 4. And then we do have a constant out front. 4 times 4 will be 16. Okay, example 8, use the graph of the integrand and areas to evaluate the integral. We're going to use both properties and graphs on this one to help us figure this out. So before I actually graph this, having the 4 plus in front of that semicircle is going to kind of mess me up and make my problem a lot more difficult. So I am going to go ahead and use the property which says if we have a plus sign that we can separate the integral. So I'm going to separate the integral to look like this. Okay, so then we can work both integrals separately. Okay, the first one, we know that the function 4 is just a straight line up at 4, and we want to find the area under the curve from -5 to 5. Okay, so we can easily see that that's just a rectangle, so just length times width. The distance of the length would be 10, and the width will be 4, so this area would be 40. And then we're going to be adding this next one. Well, we learned from the previous video that when you see something like this, it's just the semicircle, and it has a radius of 5 because 25 would be r squared. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. It's going to be a half circle that looks like that, and we want to find the area under the curve from -5 to 5. So this time we get to find that whole half circle. So the area of a half circle is 1/2 pi r squared, which in our case will be 1/2 pi. The radius is 5 squared. So that would be 5 squared is 25. This would be 25 halves pi. All right, so my final area, I just add them together. It would be 40 plus 25 over 2 pi, and that would be it. So hopefully now you are able to use properties to evaluate integrals.